Have you ever wondered how those beautiful hatched shadows you see in manga or anime could be recreated inside a game engine? Although there are already some great solutions out there, Blender, for example, can pull off amazing results for rendering this kind of stylized shading. But here we're going to try to recreate this effect in Unreal Engine. Of course, the ideas we'll explore here can easily be adapted to any other real-time rendering engine. Now at first this effect might look simple, just lights reacting to light. But once you dive into the details, it's a bit more complex than it seems, and we'll see why. So in this video, I'll walk you through my process, how I approached it, the challenges I run into, and how we can make a hatch shadow effect that feels both stylized and convincing. Let's get started. Here we have our test scene. It's a simple model with some props and a floor. So what we're going to do is start by desaturating the scene color. So first we're going to have to create a pause process volume and assign it a pause process material. So if we look for a material, we can assign a material that we freshly created and everything is black. Well, it's because we have to at least feed the scene color as it was before. So for that, we use the pause process input 0 of the scene texture node. And we'll start by essentially desaturating the scene color. Now we obtain a grayscale of our scene. We can push it further and step this value to get color bands. So we're going to bump up the light a little bit. And what we can do is now select bands based on a set threshold on which we're going to apply the hatch texture essentially. So we're going to project a texture in world space, and then we're going to apply this texture onto the color bands that we selected. So we need a mask for that so we can get this result and compare it to a certain threshold. What we essentially have here is a mask of the two bands that we just mentioned earlier, and we can multiply them back by our desaturated scene color to get the filtered bands. Then we need to project a texture in world space, so we use the world align texture node. And what this essentially does, it does a triplanar projection in world space, and this is pretty much the only way we have, at least the easy way we have to project a texture in a pause process material, because we have access to the world normal texture, which stores every pixel normal in world space, so we can project it in the world. And now we just have to multiply back by our previous mask, like so. And now, since it's still in grayscale, we can multiply this part by our scene color to get the shadows of our model. And we'll do the exact same thing for the normal non-shadow parts. So the other bands now are pitch black. And what we can do is multiply the scene color by our desaturated scene color to get this step effect. So this is the model without the shadows, and we can use our hatch shadow mask to lerp between the unshadowed object and the shadowed object. And that's pretty much it. Now we have believable shadows that react to light. So if we change the light intensity, we see that it reacts with it, and we get this really nice manga anime style hatch effect. So we can change the hatch texture for different effects, but essentially also, since we multiply by our scene texture underneath, it captures the intensity of light and the crevices as well. So that looks like it's the end of our shader. We managed to correctly project our texture in world space, and it reacts to light. However, there's some issue, and it will become pretty obvious once we start to move this object. So for static objects, nothing looks wrong. However, if we move the object, we can see the texture kind of sliding on top of the model. And this is because if we move the object, for example, in this case, in the X direction, well, the projection on the XZ plane is such that the texture is moving. And the reason is because, the texture is not really moving, the object is, and the texture is fixed. It's projected in world space. And so this might not be an issue for static objects because, well, they're not moving, so their shadows should not be moving, or rather their shadows will move according to light, but this will be natural. However, for moving objects, this is a problem. This kind of betrays the whole aesthetic of having those beautiful hatched shadows. And so one way to go around that, the solution would be, for example, to maybe project it in object space. And so the way I did this is essentially we use the stencil buffer. And so the stencil buffer is a screen-wide buffer where each pixel can store up to 256 values. It's an 8-bit buffer. And it's usually used for masking. So how do we assign a stencil value? We have to enable random custom depth pass. And then we can assign a custom depth stencil value. And we assign it to 254 in that case. It's for visualization purposes because it's easier to see it on the texture and for debugging. But essentially, if we, in the post-process material, if we only show the actual stencil value, well, this is what we see. This is the only object that it is writing to the actual stencil buffer so far. And so this is what we see. And the way we're going to use it is that we're going to rarely have more than 255 moving objects on screen. Well, what we can essentially do is use this as an ID. We can give a mesh a given stencil value and tell it, hey, that's your ID. And so every frame, what we're doing is we're checking which objects have been recently rendered. So we can check this on the game thread. And then once we have them, we assign them a stencil value depending on the available stencil IDs that we have. And then we're essentially writing their inverse transform. So they're transformed from world to object space into a texture. And so this texture looks something like that. So we have an RGB channel. So it's a 256 by 3 texture, 256 wide and 3 in height. And why we need 3? Well, because we only need 3 pixels per transform, right? A pixel can store up to 4 values, RGBA, and so we can store the X, Y, Z of the basis vectors plus the translation part. And then we can pack it tightly into this texture. And then we can sample it in our post-process material in order to retrieve the inverse transform of a given object. And so now if we apply our changes, we can see the texture is no longer sliding on top of the object. It's still not perfect, and we'll explain why later. Don't pay attention to the floor. It's because everything is projected relative to this object because we fed this stencil ID. We hard-coded it to 254. It's just for debugging purposes. But let's focus on this model, and we can see that right now the sliding is somewhat fixed, but there's still something weird happening, and you might be able to notice it. But if we feed, let's say, a flat texture, and so to better illustrate the nature of the issue, we essentially projected a flat texture on top of the model. And so don't pay attention to the rest. Please focus on this head model. And if we move it, we can see there's some kind of lag. The projecting is correct, right? But there's some kind of lag in between 2 frames. And the faster I go, the more noticeable this lag is. To explain this, it boils down to how Unreal Engine tackles rendering. Everything is done through 2 main threads. There's a game thread that handles game logic, like when an object is, collision, assigning stuff in the editor. And then there is a render thread, which sends commands to the GPU. And so, for example, if we take the example of a texture, well, the texture, there's some metadata that is in a U object, right? And then there's the actual texture pixel and its memory. And the pointer to that memory is owned by the render thread. And so when we want to issue a command, let's say we want to write to a texture, essentially, we cannot do it directly in the game thread. We need to issue a command to the render thread, and then on the next frame, the render thread schedules the actual action. And so usually the render thread is 1 or 2 frames behind the game thread, and that explains why we have this lag. And so essentially in our function, we have this macro provided by Unreal Engine that's called enquRender command. This essentially enables us to communicate with the render thread from the game thread and issue a command and tell it, hey, I want to do this, schedule it. And usually it will be scheduled for the next frame or the 2 frames ahead. That allows to decouple the render thread logic with the game thread logic and to essentially boost performance. So far, we're feeding the transform. So we're feeding the transform every frame on tick. And this is not, we have this lag. And so in order to solve our issue, this lag issue, we have to essentially mimic what the transform node in the material editor does. Turns out in a material editor, when we access the transform or when we use a transform node, it essentially queries the render thread in that same frame for the inverse transform of that given mesh. And that inverse transform is owned by the render thread. And so we need to perform all our calculations on the render thread and feed this data before the post-processing stage. And there's a really cool way to do it, and Unreal Engine gives us the code. It's just not so well documented. But there's this thing called fSceneView extension, which allows us to inject behavior before a certain rendering stage. And so the way we're doing it is we're injecting behavior before the post-processing stage. So let's quickly skim through the code of that fSceneView extension. So first thing we have to do is inherit from this fSceneView extension base class. We have those functions that we have to implement from the interface. I mean, we can leave them empty, actually. The only one we're actually overriding are those two. Begin render view family and pre-post processor render thread. And begin render view family, we could actually ignore it because I'm not actually doing anything, but it's just a debug statement to prove that it's actually being registered. And we have this function, which is the most important one. We're not using the graph builder nor the inputs, but what we're really interested in is the view here. So I'd like to preface that this whole code, everything will be bundled into a plugin that you can find in my Patreon, but I'll make sure that it's clear enough that you can reproduce it on your own. I'll include code snippets and screenshots of the material editor setup so that you can reproduce it on your own. And so this is the core function here. So the underscore render thread means that this needs to be called on the render thread, and it's actually called on the render thread. We don't have to call it ourselves. We'll register the extension later. We'll see how. And so we have this view. And so I am passing so I have a world system that is attached to this extension, and I'm checking if it's valid. If not, we return. We need the view to be a view info to get some data, special data that we need. We'll see just a little bit below. So we cast it, and then we also get the scene from the view family. And we have a list of proxies here. So if it's not clear enough, proxies essentially are a mimic version of every U object. So every U object has a proxy, which is a duplicate of that. It's not clearly a duplicate. There's kind of a mimicked version of that object on the render thread with its own copy of the data. For example, an object might have its own transform and its own copy of the position and other data on the render thread. And the reason it's separated is because the render thread is also 1 or 2 frames behind, so it holds its own copies of this primitive data so that it renders the frame in its own scope and doesn't bleed onto the game thread. So proxies are essentially a representation of a U object on the render thread. And so we reserve the memory, and then we use this fScene setBit iterator, which allows us to iterate through only the visible object. So we have this view info primitive visibility map. So it's an fScene bit array. And this is pretty convenient because we can skip a lot of useless conditional logic by just iterating through the visible objects. And so we get the index of the primitive, and then we access the primitives array of the scene, and then we just give it the index, and we add this. So we get the proxy of this primitive, and we add it to our actual proxies array. And this proxy should render custom depth, as we saw, because otherwise it would not be able to write to the stencil buffer, and we need it because we need an actual ID. And so we have this utility, stencil and matrix, which just stores stencil and a world to local matrix that we compute on the fly. So we get the local to work from the proxy. So this is essentially the same. So at this point, the transform we get is roughly the same as the one we would get in the material editor when we call the transform node. And so you can pause here to read if you want. And we get the texture from the subsystem. So this is a custom function. This is our own subsystem. And we get the resource from this texture, which is kind of the handle on the render thread of that resource, of that texture, sorry. And then we get this get texture to the render hardware interface. This is what this RHI stands for. And this is essentially a handle to the GPU memory that is also owned by the render thread. So we need this to actually write to the texture. And we get this handle, and then with this handle, we can get the width and the height of the texture, and then we can lock it. So why do we need to lock anything here? It's because we're going to communicate with the GPU, and we need to tell it, hey, I'm going to write to memory, this memory location, don't do anything. Don't read it, don't write it, because I'm going to modify it. Here I'm explaining a little bit how matrix convention and how matrix is packed in Unreal Engine. And essentially we packing those 3 columns into 3 different pixels. And finally, well, we iterate through our array of structs, and we write to the, essentially here we're writing to GPU memory. We get a pointer and we write to it our matrix columns. And we unlock it. And at this point, every frame, those changes will be committed. And how do we register this extension? Well, if we go to our subsystem, on initialize, this is the function that we need to call. We need to call this fsceneView extensions got new extension, and we initialize it with this. So this is a subsystem, and if we look at the constructor, we specifically pass a weld subsystem of type U stencil matrix LUT subsystem that we just get, and that's pretty much it. And then on deinitialize, we need to call reset as well, so that it just resets it and doesn't keep itself in memory. And that's pretty much it. That's the core aspect of the extension. And now, so if we detach and then move, we see there's no sliding. And to make sure that there's no sliding, we can just assign back our texture as before here. And then once we move it, well, the artifact disappeared. And this is because we're actually writing to the, so it's like perfect projection in object space, but we're accessing it in a post-processed material. And so that's really convenient because we can do a bunch of other cool stuff like the shadows. And so now when the model rotates, so we'll put back our previous texture hatch. Here we go. And so if our model turns, we see that there's nothing weird. And now it reacts to light. There's nothing weird. I mean, it's still sliding on the floor, but that's because everything is aligned according to this object. And that's because we hard-coded the stencil ID to 254. But once we change it, it's gonna solve it. And so for now, and now it works. And we're not using any transparent material. There's not a lot of like complex expensive calculations. It's a bit tricky to get around Unreal's documentation and extend essentially and inject behavior in the rendering pipeline. But once you kind of know a little bit, it's you kind of understand the strength of this engine. In this channel, I'll try my best to demystify some cool behaviors because I believe this is a wonderful software. I really enjoy using it, but I feel like some of the cool stuff is hidden away. I'm also working on a custom Niagara data interface for like a grass interaction shader where we can add objects to be interacting with grass pretty much infinitely. But this is for future videos. I'm still working on it. I hope you liked this video. I hope it was not too confusing. If anything, I will put screenshot of the code and the setup, the material setup, and everything in the description. And for those who want to access the barebone plugin, I will make it available on my Patreon. If you'd like to support me, that'd be immensely appreciated. But for those who can't afford it, who don't want to, I'll put all the screenshots with explanations and so that you can reproduce it on your own. Yep, that's it. I hope you liked this video. Thank you so much for watching and for sticking with me. And I wish you happy coding. Take care, everyone.